It seems that everybody muted.
Yeah, I'm not muted, I don't think.
Ah, okay, good. Okay.
So should I share my screen?
Yes, yes.
Okay. Oh, I need to change system preferences. I need to quit Zoom and start over to share the screen.
You sure?
Okay, I'll be right back.
Okay, good luck.
Rami, did you share the slides meanwhile?
No, I didn't get them.
Okay, I can do this.
I'm sorry, I just had a meeting until right now. I now see an email from you with the slides.
Okay.
2 hours ago. Yeah, I'm sorry, I was just in a meeting until.
Can you hear me now?
Yes.
And let me share the screen. Okay, here we go. Okay, can everybody see my screen?
I can.
Okay.
And I'm sharing your slides with everybody.
Great.
So.
Okay, so we can start, Dima. Okay, so we're happy to have Iordan Ganev here from here. And you see the title. So let's start.
Okay, thanks very much for the opportunity to speak here. So this is my first Zoom seminar. So if there are any technical glitches or anything, feel free to stop me. And also feel free to stop if you have questions at any point. So this is the outline. So I'll start with a few words about the context of this work and some motivation. And then I'll set things up with some filtrations on the algebra of functions on a group and the algebra of differential operators on a group. And then we'll move to more geometric things, the HOROCYCLE space, Vinberg semigroup, and wonderful compactification associated to a reductive group. And then I'll talk about some of the results and relations to other work. So this talk is based on joint work with David Ben-Zvi. We have a preprint on the archive, and we're working on a new and improved version that should be up fairly soon. So let's get started. So in this talk, G will be a connected reductive group. I'll be working over C. And if we have a connected reductive group and a smooth G variety, then one thing we get right away is an infinitesimal action of G. So this is a map of Lie algebras from the Lie algebra of G to the vector fields on X. And this map of Lie algebra extends to an algebra homomorphism from the universal enveloping algebra to the algebra of global differential operators on X. So this will be my notation. So curly X will be the curly D will be the sheaf, and the straight D will be the global differential operators. And so, and this is, this is related to the moment map from symplectic geometry, from the cotangent bundle of X to the dual of the Lie algebra. And this algebra homomorphism gives rise to a localization functor, which goes from the category of modules for the universal enveloping algebra to the category of D modules on X. So modules for the sheaf of differential operators. And this localization functor allows us to translate questions of a more algebraic nature on the representation theory side, on the UG module side, to questions of a more geometric nature about D modules, their characteristic varieties, and so forth. One prominent example of this localization functor is the case when G is when X is the flag variety, G mod B. So this is known as Beilinson-Bernstein localization. So we start with UG modules, and the localization functor goes to D modules on G mod B. And if we restrict our attention to UG modules with trivial central character, so we look at that full subcategory of UG modules, then this localization functor restricts to an equivalence of abelian categories between UG modules with trivial central character and D modules on G mod B. And this equivalence can be extended to some non-trivial central characters by considering twisted D modules, and I'll say something about that later on in the talk. So, so one application of this theorem is the proof of the Kazhdan-Lusztig conjecture on multiplicities of simple modules inside of standard modules for the Lie algebra G. So localization is a powerful tool, but there's some issues involved. So one issue is that it's not really functorial. So if you have a G equivariant map between smooth G varieties, X and Y, then there are lots of functors that go between D modules on X and D modules on Y, but none of those functors in general will make the diagram commute when we consider the localization functors. Is there a question? Oh, maybe not. Okay. So, but in certain situations, you can consider categories of D modules with extra structure over here and over here, and then you can produce a functor that commutes with localization. So actually, that's what I'll discuss later on in this talk, specific instance of this. So in this talk, we'll actually be interested in the action of the double of G, G cross G. And there'll be a few specific spaces we'll be interested in. One is the action of G cross G on the group by right and left multiplication. And as we'll see, this action is related to matrix coefficients. And we'll also be considering the action of G cross G on Y, the HOROCYCLE space for G, so I'll define that later. And this localization functor will be related to Beilinson-Bernstein localization. It'll be a doubled version of it. And we'll also be considering the action on the Vinberg semigroup, which again, I'll define later on. And the Vinberg semigroup interpolates between the HOROCYCLE space and G. So the HOROCYCLE space is a degeneration of G, and the Vinberg semigroup exhibits this degeneration. More specifically, the Vinberg semigroup forms a family over A to the R being the rank of the group. The generic fiber is G, the fiber over 0 is HOROCYCLE space. The fibers over partial intersections of coordinate hyperplanes are also interesting. I'll touch on those later on in the talk. So, yeah, so now I want to make a little aside. So I want to mention a few ideas from harmonic analysis on hyperbolic space. They're not directly relevant to the talk, but they give some context and inspiration. And it's a setting where the results are parallel and it's easier to visualize. So I'm not an expert in this field, so I'll be a bit vague. So first of all, we think of hyperbolic space as a homogeneous space for PSO2R, so quotient of PSO2R by SO2R. And we'll be thinking about the Minkowski model of hyperbolic space. So it will be a sheet of a hyperboloid. And we also have the light cone. And we'll set Y to be a different homogeneous space for PSO2R. It'll be PSO2R mod 2 by 2 unipotent upper triangular matrices. And this will be the light cone minus the origin. And this is, this can be identified with the space of HOROCYCLEs in hyperbolic space. So that's why it's called the HOROCYCLE space. And we can think about taking all those sheets of hyperbolic space together with the light cone and just take away 0 again. And that's what I'll call V on this slide. And V naturally forms a family over the non-negative reals. And the generic fiber is just hyperbolic space, and the fiber over 0 is y. So there's also a free action of the positive reals on V that just takes you between the different sheets of each of which is associated with hyperbolic space, and then it scales on the light cone. And if we think about the quotient by that free action of the positive reals on V, we get the usual compactification of hyperbolic space as a disk. So in this business, people are interested in taking functions on hyperbolic space and translating them into functions on the horocycle space, because it's somehow easier to think about functions on this cone, especially if they have certain equivariance properties. And so very roughly speaking, you can take a function on hyperbolic space, and when I say function, I really mean some sort of generalized function distribution, and you can extend it to a function that should be the positive reals, not the non-negative reals. So to a function on all the sheets, so the interior of the light cone, and this function will satisfy the wave equation. And then there's a machinery called scattering theory that lets you extend to the boundary, to the full space V. And from there, you can restrict to the space Y. And the functions you get will have various equivariance properties. And so this is known as the horocycle transform. So in this talk, let me kind of explain the parallels. So in this talk, a main character will be not hyperbolic space, but the group G as a homogeneous space for G cross G. Also, the horocycle space Y will be a homogeneous space for G cross G, mod something that has unipotent stuff in the kernel. And instead of this space V, we'll have the Vinberg semigroup. And instead of the compactification of hyperbolic space, we'll have the wonderful compactification of the group. And instead of functions, we'll be thinking about bimodules. But the results are somewhat parallel to what I have displayed here.
May I ask a question?
Sure.
There's a usual way to define a functor from fun H to fun Y, just integrating on horocycles. What's the relation between that operator
I think it's similar. I'm not quite sure, but I think it's a similar sort of idea, because maybe you need to go up to some auxiliary space before going down to horocycles.
I see. Thank you.
Yeah. Okay, so yeah, any other questions? I think this is the end of the introduction. Okay,
you said that we're sorry. Can you hear me?
Sure. Yeah, I can hear you.
You said you were taking as the analog of V. You're saying the compactification, the wonderful compactification of the group. Do you mean G or G cross G?
So the analog of V is the Vinberg semigroup for the group G. And the analog of the disk as a compactification of hyperbolic space is the wonderful compactification of the adjoint group.
Ah, okay, thanks.
Yeah. All right, so if there are no more questions, let me start with some of the notation. So as usual in these sorts of talks, we fix the Borel subgroup of G and the maximal torus contained in the Borel. So we have the character lattice of T, which is the weight lattice of G, and it comes naturally endowed with a root system. And the choice of B, the choice of Borel, lets us talk about positive and negative roots. And I'm going to let capital delta be the set of positive simple roots. And using the positive simple roots, we can define a partial order on the weight lattice, where mu is less than or equal to lambda if the difference is a non-negative linear combination of positive simple roots. So this, in some places, this is called the dominance order. All right, so then we also have the cone of dominant weight. So these are weights that pair with positive simple co-roots to give non-negative integers, and these are the dominant weights, and their relevance in representation theory is that they parameterize the finite dimensional irreducible representations of G. So anytime you have a finite dimensional irreducible representation of G, it has the highest weight, and that highest weight will be in the cone of dominant weights. And I'll use V sub lambda for that irreducible representation. All right, so now I want to talk about a certain filtration on the algebra of functions on G. So all of G will just be the coordinate algebra of G, polynomial functions on G. So anytime we have a representation V and its dual, then there's a matrix coefficients map that takes F tensor V to the function that takes G to F evaluated at the translate of V by G. So if V is finite dimensional, we can write down a basis for V and a dual basis for V dual. And we see that this encodes the matrix coefficients for the action of G in that basis. So if V happened to be irreducible, if it was one of the V lambdas, then we get an injection. And if we take all the V lambdas at once, then we get a nice morphism of G cross G representation. So that's the PETER-WEYL theorem in this context. Right, so here we have, so on this side we have a vector space with a direct sum decomposition parametrized by the dominant weights. And on this side we have an algebra, so a natural question is whether we get some sort of grading on the algebra. And it turns out that we don't get a grading, but we get a filtration. So we can define a filtration on O of G by setting the lambda filtered piece to be the span of all the matrix coefficients for representations, irreducible representations of highest weight less than or equal to lambda. And the reason this is a filtration is because of the following fact. So anytime we take the tensor product V lambda and V mu, then there's V lambda plus mu appearing there, but there's more than that. And since there's more than that, that's the reason why it's not a direct sum decomposition. But if something appears in that tensor product, then necessarily its highest weight is less than or equal to lambda plus mu. So that's why we get a filtration. All right, so now I want to talk about a similar sort of thing for differential operators. So G cross G acts on G by a right and left multiplication. So as I mentioned in the first slide, we get an algebra homomorphism from the universal enveloping algebra of G, tensor universal enveloping algebra of G, to global polynomial differential operators on the group. So we have this. And first of all, the image of this algebra homomorphism can be identified with UG tensor UG over the center. So that's because this copy of UG includes its right invariant vector fields or differential operators. This copy of UG includes as left invariant differential operators, but something in the center is bi-invariant. And we can use this homomorphism to define lambda filtration on differential operators given by the following thing. So we just take the image and we allow ourselves to multiply by functions in the appropriate filtered piece. So yeah, so there's a little argument to show that this actually defines a filtration, but it's pretty straightforward. Another way to think about this filtration is coming from the fact that, so first of all, differential operators are generated by derivations and functions. And for derivations, we can think about a filtration in which the lambda filtered piece takes functions in the mu filtered piece to the lambda plus mu filtered piece. And this combined with the filtration on OG gives us the filtration on DG.
So it's implicit here that the image generates the entire thing?
The image generates The image
Image.
together with OG generates the entire thing, yeah. But not the image by itself.
The map is not onto, but like the algebra. No, the algebra generated by the image. The image is in algebra, yeah, so it can't generate the entire thing. Yes, sorry.
Yeah.
But overall, it generates the entire thing.
Yeah, you just
even
yeah.
just UG do the work, yes.
Yeah, yeah. Even just one copy of it together with OG gives you all of DG. But there's no canonical choice of, yeah. If you want to just, I'll say more about this later, but it's better to think about both copies of UG at once rather than one at a time. So, okay, so I defined a whole bunch of things. So let's see how they work in the case of SL2. So here the character lattice, the weight lattice is just rank 1, so just Z. We have a single positive simple root in the integer 2. So the partial order relates to the even integers and the odd integers, but there's no interaction between the two of them. And what about the algebra of functions? Well, we can think of it as the quotient of the polynomial algebra on 4 variables. So these A, B, C, and D are really the matrix coefficients for the action of SO2, the defining representation of SO2, the two-dimensional defining representation. And we have the condition that the determinant is equal to 1. And note that, okay, so in order to think about the filtration, first we put the grading on this algebra where all the generators have degree 1. And then we take the quotients, and that gives us a filtration, the appropriate type of filtration, because this is something in degree 2 and this is something in degree 0, so it's fine. And what about differential operators? Well, first of all, in order to talk about differential operators, in order to write them down, we need to choose, we don't need to, but it's convenient to choose, to make a choice between right and left. So let's choose right invariant vector fields. We choose, yeah, this is the copy of right invariant vector fields, and then we have the smash product. So differential operators are the smash product of functions and universal enveloping algebra. And so now, what does this algebra homomorphism look like? Well, if we start something on this, in this coordinate, it's already right invariant. So it just includes as itself. If we start something in this coordinate, then it's a left invariant vector field, or if it's in Lie algebra, it's a left invariant vector field. And we need to write it in terms of right invariant vector fields. So if you do the combination, the computation, then this is what you get, where E, F, and H are the standard generators for SL2, and this X is just any element in the Lie algebra. So once again, this map maybe doesn't look so canonical because we have these weird formulas, but in fact the map is canonical, this decomposition is not canonical. And also following up on my remark about the center, so in the case of SO2, the center is just generated by the Casimir. And you can check that if you do this map, apply this map to the Casimir in the first coordinate, and then compute what you get, and then compare that to what you get if you had the Casimir in the second coordinate, you get the same thing.
So what does this star stand for?
Smash product.
So it's like
it's
a twisted version of the tensor product?
Sorry, what about
so
the
it's like a tensor product, like vector spaces with some
Exactly.
non-trivial structure?
Exactly, yeah. And the non-trivial structures can be written explicitly using the action of the adjoint action of SO2 on functions. Okay. Right, so now, this is kind of, now this is sort of the algebraic stuff I wanted to mention. Now some more geometric stuff. So first of all, let me define the HOROCYCLE space. So we need a bit more notation. So we have B minus, which will be the opposite Borel with respect to our chosen maximum torus. And it has unipotent radical n minus, and B minus intersect in T. Okay. So now this is the definition. The horocycle space is this quotient. So you should think of this as G cross G mod some stuff. So first of all, we take the right action of n here and then the left action of n here. Then because the torus normalizes n and n minus, we have an internal action of the torus on each of these. We take the diagonal internal action, we take the quotient, that's our horocycle space. So what's the relationship with these filtrations that I just mentioned? Well, if we take the filtration on O of G by lambda, then, and take the associated graded, then spec of the associated graded is the affine closure of Y. So global functions on the horocycle space. So the horocycle space is not affine, but its global functions is the associated graded algebra of O of G, and it's an open dense subset of spec of the associated graded, a G cross G orbit there. So this is the sense in which the horocycle space is a degeneration of G. Another important thing to keep in mind about the horocycle space is there's a residual action of T. So here we took the diagonal action of T, but there's still an extra torus worth of action. And if we mod out by that action, we get a principal T bundle to G mod B cross G mod B minus. And it's G cross G equivariant. And again, let's see how things work in SL2. So if you compute, then G mod N is just C2 minus the origin. We have two copies of that, mod scaling. So that's basically a vector and a covector mod scaling. And that can be identified with rank 1 2x2 matrices. And then this map Q, you can, in terms of matrices, it's just the matrix that sends the map that sends the matrix to its kernel, comma, its image. And if the matrix is rank 1, then both of those are one-dimensional subspaces of C2. All right, so the horocycle space is related to the associated graded of this filtration, but we can do something more sophisticated, which is think about the Riesz algebra. So to define the Riesz algebra, and here I realize I'm using two different notations for function on the group, they're the same thing, so sorry about that. So the Riesz algebra is a certain subalgebra of OG tensor, the group algebra of the weight lattice. And the way that we define this subalgebra, it's a graded subalgebra, and the lambdath graded piece is the lambdath filtered piece of the coordinate algebra, and we tack on a z to the lambda. So z to the lambda is the element in the group algebra of lambda corresponding to little lambda. So this is a standard construction. Was there a question?
Sorry, so lambda, is lambda the whole weight lattice, right?
That's correct.
Because it's kind of important here what to index your filtration by, right?
Yeah,
so it's the whole weight. Okay, thank you.
Yeah, that's a good point, because some of these filtered pieces will just be empty, and also not everything is related to 0. So one as the unit of OG doesn't appear in all the filtered pieces. Actually, I'll come back to that. So then the definition of the Vinberg semigroup is just spec of the Riesz algebra. And the coordinate algebra is a Hopf algebra. And the Riesz algebra is not a Hopf algebra, but it's a bialgebra. So the antipode doesn't work out because of something related to what I was just saying about these filtered pieces, but we get a bialgebra. And also because this is a graded algebra, we have an action of T on Vinberg, in the Vinberg semigroup. And I want to make a, first, when we consider this action of T on the Vinberg semigroup, we can choose dominant weight, a regular dominant weight, and then consider the semi-stable locus of Vinberg semigroup with respect to this regular dominant weight. And I'm going to call that V0. So, and the claim in the background here is that it doesn't matter which regular dominant weight you take, you get the same semi-stable locus. If you took something that's not regular or not dominant, you would get something different, but we won't be interested in those. And the action of T is free on the semi-stable locus. So I also want to make a historical remark that this is in Vinberg's paper on reductive algebraic semigroups. This is called SPR. And another thing is, so the Vinberg semigroup is actually a monoid because its coordinate algebra is bialgebra. But Vinberg was interested in certain categories of semigroups, and the Vinberg semigroup satisfy the universal property in those categories, but those aren't too relevant for this talk.
So I didn't got the definition of VG0.
It's the semi-stable locus, so it's an open dense subset of VG.
What does semi-stable mean?
So it's it's terminology from GIT quotients.
And just recall, so it means that the T orbits are closed, are free.
Yeah, I think I'm forgetting I could tell you the algebraic formulation, but effectively in this case, it means the torus action is free. I think in general on the semi-stable locus, the torus action will have finite stabilizers, but in this case, the action is free. So
finite stabilizers. Yes.
Yeah, and I think the stable locus has the closed orbits.
So in this case, it includes everything which is over. So it's all projected to AN. So it includes everything which is over, like outside the coordinate hyperplanes, but also other things.
That's correct. Yeah, I'll say more about that in the next slide.
But also it also includes things which are not closed orbits. Yes.
Again,
the example that the baby example that you gave before with hyperbolic space, so it will include basically everything which is not zero. Yes.
Yes, that's correct. Yeah, so it'll include non-closed orbits. In fact, this is the topic of the next slide. But first, I want to make a note here. If we look back to the definition of the Riesz algebra, and if we have this little lambda here, if this little lambda was in fact an alpha, a positive simple root, then we could include it here with the coefficient of 1. So any z to the alpha includes inside the Riesz algebra. And in fact, if we look at the polynomial algebra on these z alphas, then, so that's a polynomial subalgebra on R generators inside the group algebra of capital lambda, that includes as a subalgebra of the Riesz algebra, in other words, of functions on VG. So that gives us a map. I think this is the map Rami was alluding to just now. So this is a map from VG to AR. And we should think of this map as a family. And over 0, we have the HOROCYCLE space. That's just because, over 0, we have technically the affine closure of the HOROCYCLE space, but here I did something sneaky and replaced V by V0. And when we replace V by V0, we just have the HOROCYCLE space here, coming through the associated graded, the relationship with the associated graded. And if you unwind what's going on here with these group algebras and polynomial algebras, we see that actually this AR is a partial compactification so it's like in toric varieties, it's a partial compactification of the, not T itself, but the adjoint torus, T mod the center of G. In case I didn't say, ZG is the center of G. And then over that locus, over that generic locus, we have G cross T modded out by the internal diagonal action of the center. And again, I'll say some things about the other coordinate hyperplanes a bit later.
Well, it means that over actual each point on the quotient, you will get an actual copy of G.
Yes, that's
But
correct.
the bundle is not trivial, but something.
That's
but
correct,
it's-
yeah. So over here, if you take an actual point in the adjoint torus, the fiber will be just G. Yeah, so this map pi is flat and it has smooth fibers. So this is where taking the semi-stable locus is very useful because now all the fibers are smooth. If that's another, yeah, that's another thing. If we took the affine closure of Y, or if we didn't take the semi-stable locus, we would get a non-smooth variety over 0, but we want everything to be smooth. All the arrows are G cross T equivariant, so the G cross G action on this bottom row is trivial, but otherwise they're just the obvious actions. And yeah, T acts on V0 freely. And so now I'm ready to state the relationship with the wonderful compactification. So this is a theorem of Martins and Thaddeus, but they do much more sophisticated things in their paper. And in fact, this theorem is, a lot of the machinery is due to Vinberg. So the result is that if we take the GIT quotient of the Vinberg semigroup at a regular dominant weight, then we get the wonderful compactification, the De Concini-Procesi wonderful compactification. So yeah, and taking the GIT quotient just in this case means take the semi-stable locus and mod out by this free action of T. And it doesn't matter which regular dominant weight we take, we get the wonderful compactification in any case. Yeah, so let's look at an example. I hope I'm not going too quickly so that everybody gets a chance to read the slides, but I guess you also have them via the chat. So in the case of SL2, one can compute that the Vinberg semigroup is just 2 by 2 matrices. So yeah, it's a straightforward computation. And if we think about the diagram on the previous slide, then, so first of all, the T is just C star, and the C star action on 2 by 2 matrices is the usual scaling action. So as usual, when we compute semi-stable loci, we just need to take away 0, and that gives us the semi-stable locus. And so that's V0. And one can also compute that this pi is just a determinant map. And so then, of course, Y matches with our previous deduction that Y is just rank 1 matrices, which are exactly the non-zero matrices that have 0 determinant. And then over here, we have SO2 cross C star over the center, which is Z mod 2Z. That's luckily just GO2. Determinant non-zero. And the wonderful compactification in this case is formed by just taking these 2 by 2 matrices minus 0 and modding out by C star. It's just like taking C to the 4, mod out minus 0, modding out by C star, we get P3. And did I include? No. So I wanted to include a warning to say that in higher rank, for PSLN, for example, it's more complicated. The wonderful compactification is more complicated. The Vinberg semigroup is more complicated. I can say more about that during the questions if anybody is interested.
Can you maybe give a bit more detail about this procedure of you take GAT quotient, but you fix some character lambda? So can you just recall what does it mean?
Yeah. So anytime you have a group acting on a space in algebraic geometry, then and you have a character for the group, so it doesn't have to be a torus. It can be just any group and any character. Maybe it has to be adjoint invariant character. Well, anyway, yeah,
All right.
yeah, character, and then you take you have the notion of let's say chi is a character. You have a notion of chi semi-invariant functions. So these are functions that transform via, if you act on them with something in the group, then you don't get itself, you get itself multiplied by the character applied to the group element. And so you have this notion of chi semi-invariant functions, and you can form a graded algebra with these. So you fix your chi, and then you take powers of chi, and then so it's a Z graded algebra where the nth piece is the chi to the nth semi-invariance. So you can check this is an algebra, and then
you take the proj.
Then you take proj, yeah. So if you take spec, I think you get the chi.
You just get some open set.
Yeah, and then if you take proj, you get the GIT quotient.
But the chi semi-stable locus is the same, like general semi-stable locus is just V0G.
So when people say general semi-stable locus, they have a torus in mind, and they have like a positive something in the some generic character, because they have some sort of genericity.
You have to have some character.
Yeah, I think.
But anyhow, this would be V0 of G.
Yeah, yeah.
So geometrically, it's just V0 of G modulo T. Yes.
Yeah. That's what the wonderful compactification is, or that's one construction. There are various different constructions, but that's the one relevant for this talk. Yeah. Okay. Any other questions? All right. So now I want to move on to stating a few of the main results. So first, I need a bit of terminology and notation. So there's also we talked about the filtration on O of G and its Riesz algebra and associated graded. What about the Riesz algebra on the differential operators on G? And I'll be kind of loose here since G is affine, I'll be loose between talking about the sheaf and its global sections. So let's flash this picture up again. So when we have this map pi, it has smooth fibers, and we can think about the relative differential operators on this V0. And those are defined as generated as, so it's a sheaf, it's a subsheaf of the usual differential operators, and it's generated over functions by vector fields that preserve the fibers of pi. It's also the case that if we take this sheaf d pi and we restrict to a fiber, we get exactly the sheaf of differential operators on that fiber. Right. So yeah, so there's a natural way to identify this the Riesz algebra of dg with this algebra of relative differential operators. And so we get a functor from, so if we start with, so this would be my notation for D modules on G equipped with a filtration that's compatible, a lambda filtration, compatible with the matrix coefficients filtration on the sheaf of differential operators. So some of you may be thinking about other sorts of filtrations that you can define on D modules. I'll talk about those later. And we can define this Riesz functor in the obvious way. Okay, so one more sort of background thing I need is the notion of weakly equivariant D modules. So let me kind of go quickly here. I guess experts know this already. If you're not an expert, maybe this won't be enough information to fully absorb what's going on. But anyway, so for completeness, if we have any linear algebraic group acting on a smooth algebraic variety, then we have the action and projection maps. And an equivariant sheaf is a quasi-coherent sheaf together with more data. That data is an isomorphism between the two pullbacks of that sheaf. And so this isomorphism is happening on G cross X over G cross X. And this isomorphism needs to satisfy a certain associativity condition, which I haven't written out here. So those are equivariant sheaves. What about equivariant D modules? Well, first of all, we need to make the observation that the sheaf, that anytime we're in this situation, the sheaf of differential operators has a natural K-equivariant structure. So there's a canonical choice for this isomorphism. And now, if we have a D module, then to say that it's weakly equivariant with respect to K means that we equip it with an isomorphism between these two pullbacks, the same thing that we did here, except now this isomorphism has to be of OK box tensor dx module. So over here it was just OK tensor OX. Now we use this dx action here, and there's also an associativity condition. And strongly equivariant, which I don't need, but let me just say it, is when you put dk here. Okay, so yeah, so those are the things that we need. So now let me state the main result. So since we're going to go back to talking about the HOROCYCLE space V0, so they have actions of T, we can talk about weakly T equivariant D modules on them. And so this is the main result. So it says that basically if we define everything in the right way and put all the structure that we need, then we get that localization commutes with appropriate functors. So if we localize, so first of all, if we localize UG tensor UG modules to G, then we naturally get things that are filtered. If we localize them to the Vinberg semigroup, then we naturally get modules for the sheaf of relative differential operators, and those modules will be weakly T equivariant. And if we localize onto the HOROCYCLE space Y, we naturally get things that are weakly T equivariant. Let me make a aside to say that in this context, weakly T equivariant is the same as monodromic. So maybe you've seen the term monodromic. There's also other terms that are floating around that are related, but these are monodromic D modules. And this Rees functor that I had from 2 slides ago commutes with localization, and this restriction to 0 here also commutes with localization. So we get a composition, which is an asymptotic functor. So basically the picture to have in mind is this picture I'm always flashing. The Vinberg semigroup is a family over A to the R. The generic fiber is G, special fiber is Y. And now on the level of D modules, we have a procedure to go from D modules on G to D modules on Y in a way that's compatible with localization. So part of the proof of this theorem is just checking that everything lands in the right category. I do want to make a remark about the idea behind why the diagram commutes. So first of all, as I said before, if we take relative differential operators, restrict them to a fiber, then we just get differential operators on that fiber. And if we restrict this, the Rees algebra of differential operators on G to the open locus, then we just get the relative differential operators. So now we can just compute. If we have UG tensor UG module M, then if we take its localization to G, and then an asymptotic. So if you have the PDF open on your computer, you can go back and check what's going on in the diagram. Then when we write things out, we get this. When we write out the definition of Rees, we get this. And now this part has no lambda, so we can bring in the lambda, put things together, put things back together, get the Rees algebra of dg, restrict to y, and using these facts here, we get just dy. And that's the localization functor applied to M for Y. Okay, so yeah, and I think we use exactness at various points, but I think this is enough for now. So we also have a result that gives a geometric picture for parabolic restriction using these players, the Vinberg semigroup, and so forth. So if we have a subset, so we'll go kind of quickly here with all this notation. So if we have a subset of the positive simple roots, then we get correspondingly a parabolic subgroup of G and its unipotent radical. We have the Levy quotient and its center. And we also get a point in this affine space that's a representative point for a partial intersection of coordinate hyperplane. So its ith coordinate is 1 if alpha I is in this subset capital I, and it's 0 otherwise. And if we think about, so we have the Vinberg semigroup mapping to AR, and we have this point in the base, and if we think about the fiber over this point, then inside the fiber, as an open subset, we have this partial horocycle space, which is defined similarly as the usual horocycle space, but we just have Ni instead of N, and Li instead of the torus. So that lives over EI. And with the usual horocycle space, we had a principal T bundle to G mod B cross G mod P. Here we don't have a principal bundle, we have a fibration Li over this product of partial Phi varieties. So now if we pick a point in this partial horocycle space, then its image under this map Q is a point in this product. So we can think of points in these products as parabolic subgroups that are conjugate to our fixed parabolic subgroup. So P is conjugate to Pi and P prime is conjugate to Pi minus. Also, the choice of Y gives us an inclusion of this Levy inside of Y. And now we go back to thinking about this P and P prime. So if we think about P, there's the parabolic restriction functor from, oh, this should say modules. Sorry, this is a functor between categories. So UG modules, we first think of the UG module as a UP module, and then we take co-invariance for the nilpotent radical. So NP is the nilpotent radical of P. Okay, so that's a lot of notation. And the result is that when we get these two parabolics, so P is conjugate to Pi, P prime is conjugate to Pi prime, then we can perform the parabolic restriction functor from UG tends to UG mod to ULI mod tends to ULI mod. So that it canonically lands here. So the levies of these P's can canonically be identified with L sub I. And on the other hand, we can do the localization onto DG and localization here onto DLI. And we can construct a asymptotics functor from DG filtered modules to weakly ZI equivariant modules for this levy. Let's see, yes. Now, I want to just mention some of the ingredients of this proof. I don't want to talk too much about it. But the first ingredient is that this procedure of localization is actually closely related to covariance. So if you take any group acting on a smooth variety and you perform the localization of a UG module V, then what you're doing is actually computing the co-invariance for V tensor functions on X, the sheaf of the structure sheaf on X, and these are co-invariants with respect to the kernel of this map of, I guess, Lie algebroids from G tensor OX to global vector fields. Or maybe it should be, yeah, okay. Maybe it should just be the tangent sheaf, not global sections. Anyway, that's one ingredient that connects the co-invariants. And also there's a commutative diagram similar to the one I displayed with the main result, but here we have YI, the horocycle space, this partial horocycle space. Okay, so I think that's all I want to say here. Now I want to talk about relations to other work, just to put this work in a bit more context. So first of all, I want to say some things about Verdier's specialization. So for purposes of simplicity, I'm going to assume that the group is already adjoint, so that the wonderful compactification is a compactification of the group we start with. So J would just be the inclusion. And we have R boundary divisors in the wonderful compactification, R being the rank of the group. And these have nice intersection properties which are related with this wonderful condition, which is a technical condition. And as you may be familiar with, anytime we have a divisor inside of a smooth variety, there's the notion of a V filtration. But if we look at all of these divisors at once, then we get a multi-filtration, which is a filtration by lambda on this, on the sheaf of differential operators on the wonderful compactification. Also we get an induced lambda filtration on the push forward of DG. Also, if we have a regular holonomic D module, then there's this machinery of Cauchy-War and Lagrange that lets us construct a filtration on the global sections of the regular holonomic D module. But again, here we have multiple divisors, so it becomes a lambda filtration. And what we show is that these procedures are compatible with matrix coefficients. So the filtration that we get here via the V filtration on DG is exactly the matrix coefficients I defined earlier. And this filtration on the global sections of M is when we is compatible with the matrix coefficients filtration on DG. Okay, so also I want to say some words about this construction of Bezucal, Finkelberg, and Ostrich. So there's a notion of admissible modules. So these are regular holonomic D modules on G with the property that the center acts locally finitely. And Bezucal, Finkelberg, and Ostrich use Verdier's specialization to define a functor like so. So you start with this category, and it maps to monodromic D modules on Y. So what's the relationship between our functor? Well, if we start with a regular holonomic D module M, then as I said before, this Cauchy-War-Lagrange filtration gives us a canonical filtration, so we can think of it as an object in DG filt. And then our functor is the same as their functor. So maybe this is kind of vague because it's not really a functor from here to here. We can be more precise in the context of Harish-Chandra bimodules. So Harish-Chandra bimodule is a UG tensor UG module where the diagonal copy of UG acts locally finitely, as does the center in both coordinates. And so this is the diagram. So Harish-Chandra modules are a subcategory of UG tensor UG modules. Those we can localize, and the localization, so this functor is localization, but it actually factors through filtered D modules, and then we can apply our functor to get to monodromic D modules on the horocycle space. But there's an observation of Ginsberg in this paper that says that Harish-Chandra bimodules can be directly localized to regular holonomic D modules where the center acts locally finitely, so admissible D modules on G, and then applying this Bezucal-Finkelberg functor puts us here. So this our functor is somewhat more general than their functor because theirs is only restricted to regular holonomic D modules. And finally, finally, I want to say some things about the relation to Beilinson-Bernstein localization. So if we have a lambda weight, then there's two things we can do. On the one hand, we can use the Harish-Chandra isomorphism to define a central character, so a character of the center of the universal enveloping algebra, and correspondingly, we have a central reduction of the universal enveloping algebra. The other thing we can do is think about the corresponding line bundle on G mod B, and using that, we can define twisted D modules on the flag variety. And in fact, the localization there's a localization functor here that I couldn't figure out how to put it in the slide in Beamer, but there's a localization functor that goes from here to here. And so we can do a doubled version of this. So we have two copies of this category here, and the localization functor goes to two copies of the category here. And we can pull back modules with a specified central character to all UG tensor UG modules. And since we chose the same character, they factor through the center. And then we can localize, as we were doing previously in the talk, to monodromic D modules on Y. On the other hand, these twisted D modules can also be interpreted as monodromic D modules on Y. So we have this commutative diagram. And so we can think of this localization functor as a somewhat more uniform version of Beilinson-Bernstein localization. So if lambda is regular, then we have an equivalence of abelian categories. There's also, if we allow ourselves to pass to DG categories, then there's an equivalence that can be stated here between this category and modules for a certain monad acting on this category. And that's due to Ben-Zvi and Nadler. So I think I'm pretty much out of time. Let me just flash two things I didn't get to talk much about. So, and these are future work in any case. So these constructions can, we expect to be able to generalize into arbitrary symmetric spaces and to quantum groups in a certain sense. Okay, I think I'll stop there. Thanks for your attention.
So, may I ask a question?
Sure.
Can you go back to the slide with the first result that you mentioned with a beautiful diagram with many things?
Yeah.
Oh.
There we go.
So, I think I don't really understand what is the thing in the middle.
So these are, yeah, the notation is kind of confusing. We struggled finding good notation. But so first of all, we have this sheaf of relative differential operators on V0.
On V0 relative to the projection to this affine space. I forgot how it is.
Yeah, exactly. So that's here.
Yes, yes.
Yeah, so we have these relative differential operators. And
so this is d pi is relative differential operators?
Yeah, D sub pi is relative differential operators, and D parentheses pi is the category of modules for this algebra, for this sheaf of algebras, or sheaf of rings of relative differential operators.
It's not affine, so it's not the same, yes?
Yeah, it's not affine, yeah, it's not the same.
Wait, pi is not smooth. How do you define relative differential operators?
Pi is smooth.
Pi is smooth?
Yeah, if we restrict to V0, it's smooth. If we have all of V, then it's not smooth.
Okay, so so in the middle is just d pi there, or can go again to the diagram?
Yeah.
So what is the t of pi?
So these are equivariant D modules. So we have the torus acting on V0, and these are
So equivariant relative D modules.
exactly, yeah.
And okay, and now you have such an error, which I think I should understand. It's kind of, so the error from DG field, why DG, what is, DG field, but it's like filtrated modules?
Yeah, it's filtered D modules.
And
Filtered
this error is like open embedding, I should think of. Oh.
Open, which?
Like so if instead of considering all V0, you will consider only the paraimage of T, then this RIS error will become just equivalence.
Oh, yeah, that's right, yeah.
Yeah, so I can think about it as equivalence and then some like extension by zero or like
Yeah,
some kind.
okay, yeah, in that sense, yeah. Yeah.
It just maps between the algebras or maybe between the category of D modules. Those are all functors, yes?
These are all functors.
So category of modules over the corresponding algebra. Even recent mod, yes, okay.
Yeah.
A dt of pi is a category of D modules.
That's correct.
Yeah, they're all categories, I see.
Yeah.
Okay.
Yeah.
And a simp is associated graded?
Yeah. It comes out to associated graded, yeah.
Does it have some other definition as well?
Well, to make sense of what you mean by associated graded, because these are modules for sheaves living on different spaces. So it is associated graded, but I call it asymptotics instead of associated graded because it makes you have to be careful where the various modules are living.
Right. So how exactly is it defined?
It's just a composition. So you take the RIS construction and
just by definition a composition.
Yes.
Right.
The RIS construction is not equivalence of categories.
Not in
because it's if it was entire, I don't know, if it was entire, then we don't have even a notion. Yes.
Yeah. But there's also things like
well, because you start with
and stuff that get in the way.
The RIS construction, you just start with the filtrated module and then you build this RIS module. Yes.
Yeah.
So if you have a dt pi module, then it is graded, yes, because it's have an action of t.
You can think about graded.
And you don't have these embeddings because you just have an action of the, like I think about the one-dimensional case maybe. If you have just one-dimensional torus, it doesn't just give you a way to get a filtrated object out of this graded object.
Oh, you mean going the other way?
Yes. You have a functor to the other way. It's just not. It's just adjoint and not inverse. Yes.
Yeah. It's not.
Yes, you can take fiber in generic point, and this will be a good functor to the other way.
Yeah, but there's issues with things at zero, so it won't be an equivalence.
Okay. It will be like equivalence on the image of the RIS functor. So the RIS functor will be like some full subcategory, like an embedding.
Yeah, I think so. Yeah.
No, Rami,
yes.
Just if you consider the action of GM on affine line, then equivalent vector bundle on affine line, it is the same as filtered vector space. Just the same thing. Just at zero, you get filtration.
Yes. So this is why I expected the RIS functor to be an equivalence.
Equivalence of what?
Of categories. So in the example that you just gave now, this RIS functor is an equivalence of categories, yes?
No, it's not quite, because I consider only vector bundles, not
only vector bundles. So this is how we have to think.
Okay,
so there should be some.
This example shows everything.
I see. So this is equivalence, and if you consider shift, so you just have pair of adjoint functors. Yes.
Yes.
Okay, now I understand.
Yeah,
Can I ask a question?
sure.
So still on this diagram that's on the right-hand side of the filtered, which
Yeah.
seems to be, it's an additional structure on the category of the D-modules on, on G. So that depends, the filtration structure really depends on the choice of the positive root systems.
Yeah, the way I've set it up, yeah.
On the left, on the top, and also left, which doesn't, the categories does not depend on the choice of the positive root system. So at least on the top.
That's a good point. Yeah, I guess the way I've set it up, maybe there's some way to avoid this, but the way I've set it up, it does depend. This depends.
No, it shouldn't. It shouldn't depend. Why?
Well, for example, if I have the var group and on the left-hand side and on the top, and that's but the var group will change the filtration or something. But if you forget just from the filtered category, you forget the filtration, go down to actually G modules. That gives the functor. But the functor, the asymptotic, really doesn't descend down to that part. It's only from the filtered.
Yeah,
so regard the basic filters is some sort of a covering of the category of DG, the DG.
Yeah.
Am I correct in this way of understanding the diagram?
I think so. Yeah. Yeah.
No, I mean, what exactly depends on it? I mean, you don't really choose a positive root system, right? You take the canonical carton, which is
yeah, the carton is okay, but the choice of
the carton is okay. No, but the carton with the choice of a positive root system is completely canonical, right?
There is no canonical choice of a positive root system.
I don't think.
No, there is. It's the Borel modulo. It's in both.
Well, you have many different choices of Borel, and you can have a var group.
But the quotient by the you do, but the isomorphisms between them preserve the positive root system. So
well, if you fix the positive root system, but on the top and on the left-hand side, there is no specific indication of a choice of a positive root system or positive of the Borel.
But the point is the positive root system is not canonical only when you consider it on a cartan subgroup. But here the cartan is not a subgroup; it's a quotient of the Borel, and then it's completely canonical. It's what Joseph calls the cartan, right?
Is that in the construction of the Y?
I think the question is about this part, the filtration. So the definition of the filtration requires a choice of positive simple roots, and that part is not canonical. But of course, if you choose different Borels containing the same torus, then you get equivalent categories.
You can use the var group to.
Yeah, there's a vowel group. So there's some sort of vowel group symmetry going. I don't know this precisely, but there is some sort of vowel group acting, vowel group symmetries over here on these guys down here. But yeah, I don't want to elaborate too much on that.
Okay, well, thank you very much.
No problem. Thanks for the question.
No, I mean, sorry, so shouldn't this filtration be simply the same as the filtration attached to the boundary divisors of G within its wonderful compactification, which is completely canonical? You just take a bunch of divisors and it gives you filtration.
Yeah.
It's the same filtration, right?
Yeah, I guess. Yeah, that's a good point.
So it's all completely canonical. It's.
Yeah, actually, maybe you're right. Yeah. I think maybe you're right, because yeah, you can just think of it through the wonderful compactification picture with the boundary divisors, and then yeah, I'd have to think about it, but maybe you're right. Yeah.
And when you have a torus, when you talk about the semi-stable, you really need to have a choice of the, for the one-dimensional torus, you need to have a choice of which side is positive. To define what semi-stable means. You could go the other way. So that's the choice of where the simple roots.
Yeah, so maybe there's something subtle going on. Yeah.
It definitely is very interesting. Okay, thank you very much for a really nice talk. I really appreciate it.
No problem. Thanks for listening.
Okay. Any other questions? No? Okay, so let's thank the speaker again.
Thanks.
So, Dima, do you remember who is next week?
Yes, next week we have Shahar.
Shahar. Okay, great.
And also we have Galdor on the Friday, so we have 2 talks next week. And then we have Steve Miller on June 10th. So see you all next week.
Bye.
Okay, bye. Thanks.
Bye. Thank you very much for the wonderful talk.
Thank you.
Really enjoyed it.
Thanks. Bye.
Bye.